So next up we have our guest lecturer for the day, who's Pieter Abeel. Pieter is a professor at Berkeley, where he was my PhD advisor until very recently.
1 week ago?
Approximately 1 week ago, yep. And so Pieter is was like one of the pioneers in just applying machine learning and robotics in general. And in particular, recently he's been focused on deep reinforcement learning, generative models, meta learning, so like kind of many of the really exciting areas of machine learning that that many of you have probably heard of. In addition to academic work, Pieter has founded a couple of startups. He started Gradescope with Sergey, who presented a couple of weeks ago. And more recently, he started Covariant, which is applying AI to real-world problems in robotics. So very excited to have Pieter here. Welcome.
Thank you. So in this session, what we're going to do is we're going to talk about research directions. And so maybe the first thing you might wonder is, why even talk about research directions? Maybe you just want to build a system that works. But it turns out in AI, the kind of time between a new research result coming out and it actually being put to use is extremely short. And very often, kind of the best systems today use a lot of results that didn't exist 2 years ago. And so keeping up with the latest research actually really matters to build the best systems today. It's pretty much unavoidable. New visitor? So one of the places you can learn a lot about research is arXiv. Maybe we'll do a quick raise of hands. Who has read an arXiv paper in the last week? Everybody within the last week. Wow, that's amazing. OK. Who has read all arXiv papers that came out the last week? So nobody, I suspect, I hope. It's impossible. Here's a graph of the number of papers coming in arXiv starting in 2012. This one runs till 2017, but it's shooting up at the end. Curious where it's now. 2012, per month, there was about 200 papers coming out on artificial intelligence. And then by 2017, it was going up to 2,000 papers per month, which is just not something you can very easily keep up with. One thing I want to do here is give you some ideas of what are some of the directions that I think are very exciting, going to make a lot of changes in the near future in how we solve problems. There's a list of directions that I think are pretty important and where we'll see a lot of change, but we only have an hour and a half. So what I'm going to talk about is the first column here, but that doesn't mean the other ones aren't going to be very important too. It's just we only have so much time. But I just want to mention that now bias in machine learning is really important. And really what it often means is that if your data set is not properly collected, it'll reflect biases in your data collection process into how the system then might make really large-scale decisions, where those biases can be a lot more harmful than if it was just a single person having a bias. Long horizon reasoning is something that I would say pretty much no systems do today. Pretty much all machine learning systems deployed just make an instantaneous decision or might think 1 second ahead, but none of them do really long-term reasoning. But I think more progress will be made there in the near future. Safe learning is a pretty important one. As you actively collect data or as a physical system learn in an environment, let's say a self-driving car, you want to try something new you never tried before and see how it works. That's usually unsafe. And so the question becomes, how do you learn new things? You get novelty without the dangers of being unsafe or breaking things that are valuable. Value alignment is much further out. This you're probably not going to use anytime soon in any of your projects, but that's the notion that if we actually build really good AI that's really good at optimizing objectives we give it, we say, OK, I don't know, maximize money in my bank account or something, and it might do it really well, but it might then have sold your house. And you're like, well, that's not what I was asking for. And value alignment is exactly about that, about making sure that the way we express things, what we ask for, if it gets fully optimized for, that it actually leads to a good result, because it interprets what we say rather than taking it too literally. And then planning and learning are things that people consider very disparate these days still. Planning is, A-star search that finds a path from, I don't know, San Francisco to Palo Alto or something. And then learning is this pattern recognition thing, but in the future, they need to be brought together to build much more powerful systems. Those are the ones I'm not going to talk about this time, maybe next time, who knows. I'm going to focus on the first column here. Aside from sampling research directions, what I want to do, I want to give a bit of a summary after sampling through them of the overall research themes that come back and back and back across them. and also give some pointers on how to keep up with these thousands of archive papers that come out every month. So a first really important direction that I think we'll see a lot of deployments in the near future is few-shot learning. And few-shot here is in contrast to learning from, let's say, tens or hundreds of thousands of examples that you annotate. How do you learn from just a small number of examples? As indeed, supervised learning works really well when you have massive amounts of labeled data. But think about people. I'm looking around the room here. I'm very confident that there was a time in all of your lives where this thing does not exist, and that thing also did not exist. And then you saw it for the first time. And you just needed to see one example, and then show a new one to you. You know, yeah, that's a hoverboard again. That was easy for you. This one, it's a one wheel plus, another one wheel plus, another hoverboard. And so those things are very easy for people to learn from one example, whereas pretty much all kind of common wisdom in machine learning is you get lots of data and finally something will work. So why can we do this? How come we can actually do something that seems so contrary to what our deep nets are able to do? Well, one way to think of it is that we have a very strong prior notion of what categories are. We have seen many other things in the past, maybe dogs, maybe cats, cars, and so forth. They've been categorized. And what we've learned from that is maybe not just what a cat is or what a dog is, but the notion of what delineates a category. And then when we see one example of a new category, we might be able to reapply that notion of how we delineate a category around what we just saw and recognize something from just one example. So how do we equip a machine with such a prior? Good question. Maybe we need to show it lots of categories also. And maybe from seeing lots of categories, it can start seeing what it means to be a category and then learn from one example. So I'll give you one direction within few-shot learning that I think is particularly promising, but there are definitely other directions too. This one's called model-agnostic meta-learning. And the starting observation here is standard computer vision practice. In standard computer vision, what do people do? Well, they say, let's train on ImageNet, and then let's fine-tune on the thing we actually care about. And that's nice, because that way we might need less labels on the task we care about, because we already trained on other tasks, and the neural net has learned to extract features that are reusable across many tasks. It actually works really well. And I would say when people think about deep learning breakthroughs, sometimes there's two big things people don't think about. 2012, ImageNet, better results than ever before, but also right thereafter, hey, it turns out that you can reuse those neural nets and fine-tune them for other things. So you learn something meaningful that's reusable inside them. You might have some questions, like, how does this generalize to behavior learning? Let's say you don't just want to do image recognition, do something with behaviors. Or even just a more fundamental question. This is kind of training on one thing and hoping it'll work on something else is kind of hoping that you're going to be lucky. But can you force yourself to be lucky and force it to work on the new thing that comes later? And that's the idea I want to describe here. So model-agnostic meta-learning says, let's do end-to-end learning of a parameter vector theta, that's the parameters of a big neural network. That makes the neural network then a good initialization to start learning something new afterwards. What does that mean to learn something new? This fine-tuning thing is, well, you have some parameter vector theta, and you hope that your network is pretty ready to learn something new. Well, you get some new training data. You take a gradient of the training data loss and update your parameter vector, and you get a fine-tuned parameter vector for the new task. And if your pre-training is good, what that means is that is defined as the fine-tuning working well. So if theta prime is good for the new task, the pre-training was successful. So we can ask the question, can we force this to be true? Can we just ask for a theta such that when we fine-tune, it's going to give good results? Well, here's one way to do this. You say, I'm going to have a set of tasks. So typically I have a set of training examples. Now I'm going to have a set of tasks indexed by I. And each task will have its own training examples. Maybe one task is about recognizing cats versus dogs, another one about maybe bicycles versus cars, and so forth. So each task I has its own training examples. And what we want to find is a parameter vector theta that is such that if we randomly sample a task I, and then get to do a gradient update on the training data for that task, the resulting parameter vector, the fine-tuned parameter vector, is then good, does really well on the validation data for task I. If that's the case, then this theta was ready for fine-tuning, and especially so if that's the case for all tasks I. But this itself, you can actually see as an optimization problem. you can try to optimize to find the theta that is good at this across a wide range of tasks. With automatic differentiation frameworks like TensorFlow or PyTorch, you can literally formulate your problem that way, and it'll take care of taking derivatives through that entire process. It's pretty complex, actually, because you're expecting it to be good after a gradient update, so you're going to have gradients of gradients happening on the inside, but you don't have to worry about it. Automatic differentiation will take care of that for you. Another way to look at this pictorially is that you're trying to find in this high-dimensional space a parameter vector theta that is such that with a small gradient update on just a small amount of data, you can jump onto a good solution for a new task. OK, so let's look at an example challenge. A standard challenge for few-shot learning is Omniglot and Mini-ImageNet. Those are the two standard tasks. What happens in there is you take ImageNet, which has many, many categories, and you define tasks by taking a subset of categories and only taking the data for that subset of categories. And that would be one task. And you take another subset of categories, define another task, and so forth. And then what you get is the first task shown on the first row has some kind of bird, some kind of mushroom, dog, maybe microphone, and then piano. And then you'd hope that after seeing those 5 examples, one example maybe of each class here, that then when faced with the test set within that subtask I, you do well and know that the first one's a dog and the second one is a piano. That's what happens at meta training time. Then at meta testing time, you hope that when new categories come about, and this is a different type of dog, and other new categories that you have never seen before, that you can just see one example and also adapt quickly. And the reason you might expect this works is just like in supervised learning. In supervised learning, you have trainings data, validation data to make sure you don't overfit, and then test data. And you do well on the test data if you do this well, because the test data comes from the same distribution in some sense as the training data. Same thing should be true here. If you have task distributions, then if your distribution over task is such that at testing time, meta testing time, the distribution over task is similar as it was at training time, then you might expect this to work pretty well. How well does this work? Omniglot is a data set where there's 1,200 training classes. I mean, there's 1,200 different handwritten characters that you get to meta train on. And there's 423 test classes, so new handwritten characters you've never seen before. And the hope is because you learn to recognize the original set of handwritten characters really well, you can quickly fine-tune onto new ones. So it shows here is one shot means that you get one example of each class. 5-way means that there's 5 classes in your task, so 5 different types of characters. And it's shown that this approach I just described, which is in green, with just one example of each, 5-way classification has only 1.1% error rate. So one example, 5-way classification, 1.1% error rate, which obviously it means it's reusing a lot of things it's learned in the past to quickly fine-tune on this new problem. 5-shot means you get 5 examples of each, and then it brings it down to something 0.2% or even lower. 20-way is harder because there's 20 characters to distinguish, so the baseline rate, if you had something naive, would be a much higher error rate. You see it's still there. It learns very, very quickly from a small number of examples to classify handwritten characters it's never seen before. Then ImageNet, which is a harder task than handwritten character recognition, we see similarly that even from a very small number of examples, 5-way classification, one example of each class, is able to adapt and get an error rate of about 50%, which is much better than chance. Obviously not human-level error rate, but it's quite good. And if you get 5 examples of each class, bring it down to about 32% error rate. So you can learn pretty good classifiers from a very small number of examples if, ahead of time, you had a very large number of examples on related problems that you could pre-train on to then fine-tune from later. If you want to learn more about this, there's quite a few papers on meta-learning for classification, which is what I just described. There's a really cool demo that I actually want to show live here. Let's see if I can pull up a browser window easily. A demo by John Schulman and Alex Nichols from OpenAI. Let's see. Reptile named somewhat after mammal. related approach. So this demo is amazing. I'm going to clear this out. Erase this. So this has been trained on the omniglot data, the handwritten character set. And so the hope is that if you now define new handwritten characters or drawings, it can learn from just one example what the category is that you're drawing. So let's try this. So I'm going to draw a few things here. Let's see. Maybe I'll draw a house, some kind of house. Let's see. OK. Maybe there's even a door. OK. Nobody's going to hire me for my drawing skills. Maybe we'll draw a car. Remember, it's only seen handwritten characters before, so these are completely new things it's never seen before. Complete those wheels. And maybe a tree. Very straight tree. Wow, not so straight. OK. All right. So we have 3 categories here. What shall we draw on the right and see if we can recognize it from just one example of each category? You want the car? OK, sure. Try car again. Let's see. But I'm going to draw it a little differently. I mean, not just because I can't repeat it, but I'm going to, on purpose, not try to draw the exact same car, because we want to see if we can generalize to what it means to be a car. So now, either way, a car will have wheels. So maybe I'll already start to draw the wheels. It thinks it's pretty likely a car. It's actually very common as a car. I can only ruin this from here. Let's see. Oh. Yeah, it's becoming less confident as I'm proceeding. Maybe it's kind of hatchback car. Let's see. Oh, yeah, clearly. But clearly, it's still pretty confident. It's a car more likely than any of the other things. 54% from just one example of each category. And this is a live demo. It's not pre-programmed in any way. You can go try this yourself. You Google reptile OpenAI, you'll find this demo, and it works. Well, every live demo I've done so far has actually worked that it finds the right category. We actually use this at Gradescope, something very similar, where we build AI software to automatically grade homework and exams. Maybe Sergey mentioned something about it. Not this specifically, but essentially, well, you start grading is the idea, and there's maybe 500 students who gave answers to a question. And once you grade a few of them, you've essentially provided a small number of labeled examples, and it can generalize to the other ones that you haven't looked at yet at roughly 90% success rate, and then you can decide whether you want to keep going or whether maybe you just let the students submit regrade requests at the end, and then you fix the ones that maybe weren't perfect. And so you can save an enormous amount of time, and this is a perfect kind of few-shot learning setting, not just from a scientific point of view, but the notion that you'll design new questions, and these questions will be related to older questions, of course, because it's on the same material, and so now you should be able to reuse what you trained in the past to quickly learn to grade something new. People don't just look at meta-learning for classification, they also look at it for optimization, where you might say, well, gradient descent is human designed. Can we find something that's actually better than gradient descent? Actually pretty hard to do, but if you have a narrow class of problems, often you can still find something that's learned that's more effective than gradient descent. You can also do this for generative models. We'll talk more about those later, but the notion that you can classify something is one way. Another thing you could say, if I've learned to generate a lot of handwritten characters, and I'm now shown a new one, can I then generate a nice range of that character that I've been shown one of? OK, now I want to switch gears to a different kind of learning. Few-shot learning is about learning from a small set of examples, but often still in the classification setting. I want to switch to reinforcement learning. So here, who here has heard of reinforcement learning before? Almost everyone. Who here has implemented something reinforcement learning before? Huh, still a pretty good number. OK. What did you implement?
It was like I had a markup problem. It was not deep reinforcement learning, but I had like a markup problem. I'm an economic PhD student.
So you implement value iteration, policy gradients,
Q-learning.
Q-learning. OK. How about you? I think you also raised your hand.
Yeah, I did imitation based, and then
EDPG. Okay, great. And there was some other hands there. Anybody else there? CartPol. And which algorithm did you implement for it?
This is a long time ago. I'm trying to remember. I also did like brain-based like time difference.
Oh. Wow, okay. So we have about 5 people here, I think, who implemented RL before, which is pretty good. It turns out reinforcement learning does not have that many applications in the real world just yet compared to supervised learning. Like if you look around, the amount of use of reinforcement learning tends to be much more limited. There are places, simple reinforcement learning problems like bandit problems, which are used, of course, extensively for advertising and for optimizing news feeds. In robotics, reinforcement learning can play a big role because it can fine-tune performance on top of what you might have already learned in the past from maybe demonstrations or something you hard-coded. But in general, I would say it's kind of on the cusp of making its way into applications, but not so widespread yet. But this might be the time you can go make that difference. So in reinforcement learning, the agent interacts with the world. The agent, we can think of as essentially the brain or the software, might then make the robot and environment change state, and then there's a new state, and a new action gets taken. And this loop just repeats over and over and over, and the purpose of the agent is to maximize reward. And so the way you interact with that agent, assuming the reinforcement learning algorithm already exists, is by saying, this is my reward function. You might say, OK, I don't know. Maybe your reward function is to get a positive reward when you reach a destination as a self-driving car, and a very negative reward for accidents, and a maybe slightly negative reward as long as you're not at the destination yet. Because it might encourage getting to the destination sooner rather than later, but also encourage you to be cautious. Compared to supervised learning, there are actually a lot of new challenges in reinforcement learning. So one of them is credit assignment. What does that mean? Let's say you have a cooking robot, and you ask it to cook a meal, and now half an hour later it comes back with a meal, and it gives it to you, and you're like, 4-star meal. So OK, now the cooking robot knows that that was a 4-star meal, but what did it do right or wrong in that past half hour? It doesn't really know. They might go cook again. It comes back, and now you say 3-star meal. And you might say, well, that means something it did was better the first time and worse the second time. But there might be a mix of things. There might be some things that were better the second time, even though overall it was worse. And so that's the credit assignment problem. Then your system going in and say, well, what did I do those 2 times? And what might have been what contributed to it being better versus worse? From 2 trajectories, actually pretty much impossible. You often need thousands, if not tens of thousands of trials before you can tease apart the benefits that you get from things versus downsides. Another big challenge is stability. If you have a reinforcement learning system, it just tries things. And if there's a feedback loop like you have here, you could destabilize the system, and it might crash. And then you cannot continue to learn, maybe, and you need to fix things before things continue. Exploration is not a big one. The whole point in reinforcement learning is that you become better than what you've been hard-coded to do. And so to become better than what you've been hard-coded to do, you need to somehow try things you never tried before. And of course, that again interacts in difficult ways with stability and safety. Despite this challenge, actually, there's been a lot of progress. A big breakthrough in 2013 was Vlad and me and collaborators at DeepMind showing that a deep neural network can learn to play a wide range of Atari games from its own trial and error, repeatedly trying to play the game and just learn to maximize score. A lot of other progress on this since, a lot of it out of DeepMind, OpenAI, and Berkeley, showing that you can do even much better than they did in 2013. But that was kind of the first, I would say, the first moment that people saw evidence that a lot is possible that people didn't think before would be possible. Much like in computer vision in 2012, the ImageNet breakthrough. Then, of course, from there, DeepMind specifically took it to the game of Go, traditionally seen as a very big challenge for computer science. In fact, in 2012, when surveys went out asking how long will it take before there's a human-level Go player, the median probably landed around 20 to 30 years. But it actually only took from 2012 to 2015, so it only took 3 years. So a lot of people thought it was going to take a very long time, and it happened 3 years later. You might wonder why the mismatch? Well, for a game like Go, you can think of it in 2 ways. You can say, OK, how can I play this game? Well, I make a move, you make a move, you make a move, I make a move, you make a move. It branches many, many ways. And the many futures that are possible, there's so many of them, you cannot enumerate them. Unlike a game like tic-tac-toe in a 3x3 grid, you can think through all the possible ways of playing the game, and you can solve it in an explicit way. In Go, nobody has solved it explicitly. Nobody has provably shown that, let's say, white is guaranteed to win if they play correctly, or black is guaranteed to win. But that's how people were thinking about it back then. Another way to think of it is that it's just an image with white pixels, black pixels, and empty pixels. And if you can build a pattern recognizer that can predict whether your move is more likely to win than another move available to you, then that can guide you in what moves to make, and you can actually play really, really well. And that's effectively what happened, turned into a pattern recognition problem rather than a massive search problem. Admittedly, the pattern recognition is supervised by some shallow searches and so forth, so it's a mix of both, but that's really the big change, that you don't need to search that far. Pattern recognition can do a lot. OpenAI, around the same time as DeepMind showed Go, showed that it's possible to learn to play the game of Dota 2, which is a pretty popular video game where you play 5-on-5, but initially was also 1-on-1 at the time. Recently, also 5-on-5, where computer players can now do as well as human players. At Berkeley, our focus was really on robotics at the time, and so what we're watching here is actual learning in action. Not just the result, but the learning happening. And the neural network is being updated each iteration to become better and better and better at controlling this robot. And so in about 2,000 updates to the network, it's able to run. And the beauty here is that the way you then want to program a new robot to run, instead of thinking about Newtonian physics and what's different about this new, let's say, maybe four-legged robot you're going to get next, you just run the same code, and it can also learn to control a four-legged robot. In fact, the exact same code can learn to control learn to play the video games, the Atari games, just as well. And so what you get here is something very, very general that learns from its own trial and error, and whatever problem you put it in front of, over time it figures out how to solve that problem. Here we have four-legged locomotion, and traditionally people would work on this by very carefully thinking about contact forces, center of mass relative to the support triangle of the 3 feet on the ground, static stability, dynamic stability, a lot of considerations, and actually have a very hard time getting this to work, but with learning it can just automatically figure it out. Here's another problem, is how can you get your robot to get up? Here the reward function is distance based on distance of the head to standing head height. The closer the head is to standing head height, the higher the reward, and it figures out standing up. What we have here is a very wide range of behaviors. So this is the humanoid character again. It's been trained to do pretty much any behavior a person could do. Yes? Yeah, it's a good question. So for one skill, I would say if you were to run it on a physical system in real time and one physical system, it would take about 2 weeks with the approaches I showed here. I think we can do much better in the near future, but with the approach I showed here, it would take about 2 weeks. In simulation, you can run faster than real time. You can run many simulations in parallel. You can do it in a couple hours. Doesn't need to be humanoid characters. This is a simulated lion, and its muscles are controlled by a neural network that's been trained beforehand to make it run and withstanding perturbation forces shown with the big red arrow. You can also do it with real robots. This is Brett, the Berkeley robot for the elimination of tedious tasks. Brett lives on the 7th floor of the AI lab at Berkeley, and here is practicing Lego block stacking. This is a slightly more confined skill, so this actually takes just 1 hour for it to learn to stack a Lego block. And with these results, actually what happened next is that NASA contacted us and wanted to see if we could reinforcement learning could enable to learn to control this robot. So you might look at this robot and say, why would you build a robot this way? Why not just build a Mars rover with wheels like we're used to? Here's the reasoning. They like this format because if you extend the cables, you can bundle it together. It's a bit like a tent, effectively. The tent fits in a small bag, but then when you expand it, it's a big robot. Because it's pretty big when you expand it, then it can actually be thought of as having a big wheel in every possible direction at any given time because it's the shape of a sphere. Only problem then is how do you make it move? And traditionally what you would do is you'd think very carefully about how do I shift the center of mass? Which cable should I make shorter, longer to make the center of mass shift? And then it might tumble and repeat. They tried that for a long time, but actually never really worked. Then with reinforcement learning, you just let it run for, I forget exactly how long this experiment took to run, but probably a couple days. We actually fully trained this in simulation, and then the controller worked on the real robot even though it was fully trained in simulation. And this is actually over in Mountain View at NASA Ames. So a lot of good successes there. And so I would say reinforcement learning is kind of becoming ready to be applied if you're willing to collect a lot of data, which often is a little tricky, by the way, because while you collect data, you might break things. So in real life systems, collecting data can be a little tricky. So mastery is achieved on all of these tasks that I showed to you. But another question you could ask, how smart is the system really? When you think about people and you say, well, maybe somebody is like, I don't know, really good at something, does that mean they're very smart? Not necessarily. Like, you would probably then wonder how long have they been learning that? If they learned it overnight, they must be really smart because that's a complex thing they acquire. But if they've been doing it for 30 years, nothing but that one thing, and they're really good at it, well, maybe that doesn't mean necessarily that they're that smart. And same for these reinforcement learning systems. The question could be, how good is the learning rather than the final result? If you look at the Atari games, these plots essentially summarize how long it takes a human to learn to play a new game versus a double DQN, which is at the time, a couple years ago, the most sample efficient algorithm. And currently, there are not that many that are, I mean, it's not very different from what we have today. Double DQN takes 115 hours to become as good as a human can become in 15 minutes. So many orders of magnitude different in learning speed. So the question then becomes, how do we bridge this gap? It's going to be a similar thinking to what we had before, where we did for classification, went from classification to few-shot classification. We'll think about whether we can do something similar here. If you look at methods like TRPO, DQN, A3C, and so forth, they're all fully general methods, which means no matter what problem you face them with, they'll be able to solve it, which is nice, but they also don't have any prior information what the problem might be, and so they're not really attuned to solving a problem more quickly by having any prior understanding of what problems it could encounter. And in the real world, the environments that we encounter are a very tiny subset of the environments we can define mathematically. For example, every real-world environment will satisfy our universe's physics. But in principle, you could define other physics laws, and that would be a new environment in simulation, but you wouldn't encounter it in the real world. So the question is, can we develop faster algorithms that take advantage of this prior knowledge somehow? One way you might want to do it is you might just want to build it into it, but that's actually pretty hard. So what we're going to look at is, can we somehow have this agent learn ahead of time some things so they can more quickly learn something new in the future? So what is an agent anyway? Inside an agent, there's usually a learning algorithm and then a policy or a queue function that's being updated by the learning algorithm. The policy or queue function does the interaction with the environment, and the learning algorithm observes that, and from the sequence of interactions, updates the policy. And so in environment A, policy gets updated to be specialized to environment A. Environment B gets specialized to environment B, and so forth. Traditional RL research is really about designing that RL algorithm box. And the hope is that somehow you come up with a really good algorithm that allows you to learn very quickly. But despite many, many decades of research on this, none of these algorithms work nearly as well as compared to humans, how fast they pick up a new skill. So how about an alternative? How about instead of just learning the policy, we also learn the algorithm? Maybe if you learn the algorithm, we can learn something much better than we've been able to design so far by hand. So what would that mean? There would be meta-training environments, and the algorithm gets to interact with these environments, and from those interactions, it's supposed to extract something that then becomes a new type of agent that can learn a lot more quickly than a traditional RL agent. In environment F, it's never seen before, it should learn quickly, or G, and so forth. So how can we formalize this? Here's one way to formalize this. What we want is an agent parameterized by a parameter vector theta that is such that if dropped in a random environment M and getting capital K episodes in that environment M, it should collect high reward. If we keep capital K small, in this drawing here, capital K equals 2, that means that we expect an agent when dropped in a new environment and only having 2 episodes to already collect high reward. If it can do that, it means it learns really quickly. And how do we find this agent? Well, we can actually set this up as an optimization problem again. We have an objective, which is to find this agent that collects high reward when only have a small number of episodes in a randomly chosen environment. And then the hope would be, just like in supervised learning, that if you do really well on your training examples in supervised learning and training environments in reinforcement learning here, that you'd also do well on new environments you've never seen before at meta testing time question.
So this would depend upon how close the new environment is to the older environment.
Exactly, absolutely.
How do you figure that part out
Yeah.
as to like
So-
these are the environments I should be training on?
Yeah, so that's exactly, I would say, where a big part of the frontier, and where the frontier needs to move much further. So I'll give you some examples where this works, and you'll see that training and test environments are fairly related, which means that it doesn't generalize as widely yet as humans can generalize, but it shows some evidence that this is possible if there's a reasonable relationship between training environments and testing environments. So what can we make the agent? Maybe we can make it a recurrent neural network. Why is that meaningful? A recurrent neural network can encode any computer program effectively. And so if we think that there exists a good reinforcement learning agent out there, some kind of system that learns fast, then allowing it to be a recurrent neural network in principle should allow it to find that program that can do this for us. The weights in the RNN would correspond to the algorithm that essentially does the learning from seeing experiences, as well as the prior of what it might expect to be a good policy or what this environment might be like. And then the activations in the recurrent neural net, they will change as you act in a new environment. These activations correspond to having fine-tuned to the current environment, and so they encode the policy that you have currently. The objective itself can be trained with reinforcement learning. So you can actually learn a fast reinforcement learning agent by running a classical human-designed slow reinforcement learning algorithm. Because if you look at this objective, it's like reinforcement learning. It's just that when you start off in reinforcement learning, you tend to always start off in the same environment, possibly a random state, but the same environment. And here, you just start off in a random environment. But otherwise, this is the same kind of objective. One place we tested this is in multi-arm bandit problems. So multi-arm bandit is a problem where you have many bandits to choose from. Each bandit has a different probability of payoff, but you don't know the probabilities ahead of time. And so you're supposed to explore, see which ones have high probability of payoff, and then exploit, zone in the ones that pays off more frequently. So this is a canonical reinforcement learning problem, but in some sense the simplest one that exists out there. And it turns out that humans have designed asymptotically optimal algorithms for this. So you can rely on something like Gittins indices to optimally explore this bandit space and on expectation maximize reward. So the question then becomes, can we have a reinforcement learning agent that has learned to reinforcement learn such that it does as well as these asymptotically optimal algorithms? We compared to many of them. Gittins did the best among the provably optimal ones designed by humans, and we see that learning to reinforcement learning does about as well as Gittins. So it means that we can do as well as the best human-designed ones, which we know are asymptotically optimal, by just learning the agent, by having it face many, many bandit problems, and over time the recurrent neural network becomes really good at facing a new bandit problem it's never seen before. Here's a robotics setting, still a narrow task distribution, to your point. This is the half cheetah, classical reinforcement learning domain. The cheetah is going to always be the same. The only thing that's going to change is the task description, which is the speed at which it's supposed to run. And so a new environment means a new target speed, which we'll experience as it runs at a certain speed. It'll see how much reward it gets. It runs at different speed, it gets different reward. And you'd hope that from that it can figure out what the right speed is and fine-tune onto that right speed quickly. So here's this in action. This is the first episode in this environment with this specific reward function. And we see that from the first episode, it already starts achieving high reward. Now, to be fair, we had a lot of meta training ahead of time where it was trained to be ready to be in an environment that's exactly like this. It just doesn't know ahead of time what the reward function is going to be. Same thing for Ant Robot. Didn't play. I don't have full control over my mouse cursor. Not sure why. OK, we'll skip the end. We'll go to the next one. Maze navigation. This is a wider range of environments. This is a very classical robotics problem where you're dropped in a new environment. Can you find your way to a target if you don't have a map? And you might not even know where the target is, but you'll recognize it in this case by it being very red. So the map is shown on the right, but it's not available to the system. It's just for our purposes to see what's going on. The system just gets a first-person camera view and can steer 2 degrees to the left, 2 degrees to the right, or keep going straight. If you randomly move in this environment, this is the kind of motion you get. It's not very exploratory and not very good in general. Then after the agent has trained in many, many other mazes in the past, and every time it got 2 episodes in each maze, and then a new maze, new maze, new maze, it's now dropped in yet another new one. Let's see what happens. We actually get what we hope for. It's running down hallways looking for a target, sees a target, runs to it, and then quickly runs to the target again. So remembered enough about that environment to go to the target again. So sometimes to build an internal map of the space to go visit that same spot again. How well does it work? Here are learning curves. And these are interesting learning curves. They're not the curves that you're used to. So horizontal axis is still iterations. When you see something like this, you'd probably say, oh, it must be some train and some test curves. And train is doing really well, and test is not doing as well. But actually in meta training, where we generate our environments, every time when we're training, we generate a new environment. So train and test are not different, because while we're training, we're only seeing an environment again and again that we've never seen before, never any repeats. So these are all training curves, but with different random seeds. And the training curves, which are also test curves, because it's always a new environment, show that sometimes it doesn't work so well. You might wonder what's going on. How could it not work well? Well, one way it could not work well is that, let's say, it finally finds the target in the current maze, and then it memorizes, OK, I now know you go straight, then right, then left, then right, then somewhere straight, and that's where the target is. It gets dropped in a new maze, it doesn't work anymore. That would be overfitting. And that is easy to avoid, actually. You just make smaller updates, regularize. You can avoid that kind of overfitting. What we're seeing here is actually underfitting. It's where it just doesn't get enough signal. When it just randomly explores a maze, but it takes so long before it finally finds a target that it cannot do the credit assignment anymore. It doesn't get enough signal to understand what it should learn from this experience, and it just ends up not learning. Part of it is the architecture we used. We use a recurrent neural network, and recurrent neural networks are known, if the horizon is very, very long, that it's hard to propagate all that signal back. Usually you do some kind of, you stop the gradient, you clip it maybe at 20 steps, and 20 steps, well, if it takes 1,000 steps to find a target, if you clip it at 20 steps, you're not learning. You're not seeing what you're supposed to see. And if you don't clip at 20 steps, well, then your gradients might explode or vanish. You don't learn either. We actually looked at a different architecture called Snail. This is now 2 years ago. It's an architecture that combines ideas from wavenets, which is dilated temporal convolutions. So instead of having hidden units, we're going to have dilated temporal convolution. But also, attention is all you need to be able to see in detail what's there in the past. Because if you just use a wavenet, you would lose a lot of detail. You would not remember enough about the past. So you have both attention and dilated convolutions. With that, we can actually solve the bandits better than with the LSTMs. And we can also solve bigger mazes than we can solve with the LSTM version. So the large maze, it has much shorter times, which is better. And here's an example of a much larger maze that's solvable this way. This is an example of where we essentially run the same algorithm at a high level. All we change is the architecture from LSTMs to, in this case, attention plus dilated convolutions, and it allows the signal to propagate and learn. This is at meta testing time. You might say, why is it taking so long before it actually finds the target? Well, it doesn't know where the target is. And so we picked specifically an example here where it's unlucky in all its choices, so you can see that it is smart enough to not revisit places it's been to before. So it remembers enough, because it doesn't have the map, but it remembers enough from that past experience from the first-person vision to not revisit places it's been before. There's a lot of work in meta learning for RL also, not just the work I've shown here, but probably the maze navigation is still some of the most kind of impressive results out there. And one thing I want to highlight is the model-agnostic meta-learning that I showed earlier can actually also be applied to reinforcement learning. Here I showed a different approach, but there is some connection you can make there too. I would say the big challenge with it is, come to your question, is the environments in which we test. So people are starting to design we've had Vizdoom, DeepMind Lab, Majoko environments, but people are starting to design new contests around, let's say, video games with multiple levels. If you can get to meta train on levels 1 through 20, but then meta test on levels maybe 21 through 30. And can you adapt quickly? And so OpenAI had a contest around it. The results have not shown kind of meta learning breakthroughs yet. Maybe it's too hard, maybe it's too easy. Kind of standard fine tuning worked just fine in the retro contest that was held. But that's really one of the big challenges, how to design a range of environments such that you can meta train and generalize beyond what we've seen so far. Another way you can get a lot of signal action instead of reinforcement learning is imitation learning, where you get examples to learn from. It's actually seen a lot of success in robotics in the past. And typically in imitation learning, you get many demonstrations of something. And then from that, you extract a policy that can hopefully do well at your task. Maybe first you want to assemble a chair, give a lot of demonstrations, learns to assemble a chair. Then you want to assemble a table, a lot of demonstrations, learns to assemble a table. But that's exactly what we don't like about supervised learning. Same thing here. You need to give a lot of examples every time you want something new. Can we avoid this? Can we instead have a system like this? You see a bunch of demonstrations of different tasks. You learn the essence of what it means to be a demonstration of a task. And then in the future, you learn from one demonstration how to solve a new problem. And this could be demonstration of task F or G and so forth. All right. Here's one way to formulate this. If we want to be able to learn from one demonstration, we can formulate it as, at training time, we will have 2 demos of each task. And the first demo is the one we're going to consider that we'll have available in the future when we only have 1 demo. And so that's a whole video, let's say, that we get to look at. And the second demo we'll use for training. We'll say, OK, in each frame in the second demo, can we predict what action we should take in that situation by indexing into the other demo? And then we have a loss here. Whether we predict the correct action or not? So we can train that in a supervised way. And if you do really well at this, and then there's a new task, all you need to do is use that same neural network to index into the demo, and for the current situation, predict the action to take. I actually tested this. This was at OpenAI at the time for block stacking. So here we have a wide range of tasks. A different task means a different configuration of blocks that you're supposed to achieve. It's supposed to learn also that it doesn't matter what the coordinates are of the blocks. What ultimately only matters from the demonstration. When you see two demonstrations, you'll see they don't put blocks in the same place. But in both of them, let's say A will go into B, and C will go into D. And it'll learn that that's the thing it has to pay attention to. And we see on the left here is a video, the one demonstration it gets. On the right is the execution based on that one demo, after, of course, been trained on many pairs of demonstrations in the past. What we see here is that it's paying attention to different time slices in this video. We're watching it as a linear video, but the neural net gets to see the entire video at the same time, chooses what to pay attention to based on what it's seeing over there. And then over here, you can see which blocks it's paying attention to based on what it's seeing in this video over here, what blocks this robot is paying attention to in the demonstration. And we see it actually successfully builds the same configuration as was demonstrated on the left, but the coordinates are completely different than what they were on the left. So this is one way to formulate it. Now I want to share with you a different idea, which is how we can do this with mammal. So we're going to solve the same problem. We want to learn from one demonstration, but with a completely different approach. And I would say this is kind of somewhat typical of research in that there's often problems where people have completely different approaches, and they both kind of work, and it's not clear yet, 5 years from now, what people are going to use. Often probably a combination of both ideas, but who knows? So we saw mammal for supervised learning. Learning from demonstrations is like supervised learning. You have an input, an image you currently see, and then an action you take. And so that's a regression or classification problem. So you can do the same thing. You say, I'm going to train on a wide range of tasks, where now my training task, if I have 2 demos, one demo is the training task, the other demo is the validation task. And I want to be able to do one gradient update based on all the training demonstration data, that one demo, such that the resulting fine-tuned parameter vector performs well in predicting the actions in the second demo. If you can do that, then you adapt it quickly, and you can expect this to do well. So here's object placing from pixels. So we have an input demo, shown on the left. Somebody is teleoperating Brett to put the apple into the blue bowl. The robot at meta training time did not have a blue bowl, did not have a red apple. Those are the options on top, but these are now test targets. It sees that one demonstration. It does a gradient update based on data that's image to action. And here it is now. Asked to do the same task from the one demonstration, and it succeeds. You see it learned the concept that you need to pay attention to the bowl that the thing was dropped into, not the coordinates of where things were dropped. And it correctly recognizes that same object in the image. It's never seen that object before, but it finds it and steers the robot onto it to drop the apple. Now, question you could ask is, can we learn from just video? Usually, teleoperating a robot is pretty hard to do, and it's very tedious. So what if we can just take a video of a person doing the job and just learn from that directly? And what I want to illustrate here is a kind of very clever idea that is much more general than it is specific to learning from demonstrations. If you look at this notion here, we have a validation loss and a training loss. There's no reason they need to be the same loss. Let me make this more concrete. When we're testing, at test time, we want to just have a human having a video of a human doing the task. So the gradient update on that train, we want that to be on a video, not on a teleop demo. But when we're training the robot ahead of time, maybe we're still happy to teleop, and the validation loss can be based on teleop. And so that's what we're going to set up here. Validation loss based on teleop. This ensures that we ground it into the overall loss being about, do you take the right actions? But then the training loss on the inside is based on predicting the next video frame. So what does this look like? Pictorially, we'll have a neural network with two heads. One head is predicting the action. The other head is predicting the next frame you'll see in the video. And the hope is that if you get one demo of just a video, if you do training along this path to predict the next frame better from that one demonstration, that the backpropagation happening here and resultingly also updates happening here will be such that if then you forward propagate this way, you'll get the right actions on the second demo that was a teleop demo. This is a very general idea that you can essentially end-to-end train where you have one type of data that's easier to get maybe in the future, another type of data that's harder to get, but you can get some of it when you're initially training your system. And you can set up a network with two heads, and you can actually train it specifically that when you collect that easier to collect type of data, that it should result in also becoming good on this other output. And so it's different from just having an auxiliary loss. An auxiliary loss, you just kind of train two losses at the same time. But this, the objective is set up that training along this path is supposed to help that other path specifically. Yes?
So how's this different from, say, transfer learning?
So this is a type of transfer. So transfer learning is about when you learn on one problem, how do you learn then quickly on another problem? This is essentially end-to-end transfer learning, where instead of just saying, I'm training on one thing and I hope it'll transfer well by choosing a clever architecture or something like that, here it's saying, well, I still need to choose a clever architecture. It's also setting up an objective that says it has to transfer. So at training time, you're forcing it to transfer, where you learn along the bottom path should transfer to doing well on the top path. And you're exactly right. This is in the context of imitation learning. We could imagine doing this in very other contexts. Like, I don't know what it would be, but maybe it would be something along the lines of, I don't know, making this up on the spot. But maybe you like to annotate animals where their head is and their legs and so forth. But at annotation time later, all you want to do is annotate the head. You don't want to worry about anything else. But you want it to be the case that if you get one example of annotated head on an animal, that the backpropagation leads to, on the other path here, that it also automatically starts finding the legs and the tail because it's seen for this animal, this is where the head is, so then usually the body's like this, and maybe I can also predict where head and tail are along the other path, where body and tail are on the other path. A little extra thing we need to do actually, if you try to do it this way, predicting pixel values is actually not a great loss. Because imagine your robot is trying to do something, and it's paying attention to this video of a person, and the person is doing something here with their hands. There's so much else happening, and predicting all the details of the pixels makes you pay attention to a lot of things in the image that don't matter for the task. And so what you can do instead of trying to predict pixels, you can say we should have a different loss function. It should pay attention to things that matter, the placement of the objects and so forth. Maybe you can design it by hand, but we actually didn't want to do that. We actually learned that loss function. So we specifically said we're going to learn a loss function that is such that if you use the learn loss function and then do a gradient update against the learn loss function, then it does well on the other path. This is a lot like generative adversarial networks, where you have a generator and a discriminator. You can think of this as the discriminator here, whether in some sense the image generated here, the discriminator is happy with it or not. And then you backpropagate through that to get good performance on the top. Here's what happens. Now, the robot just watches the human do it. And then after that, the human puts things in a different place, and it actually does the right thing.
What is the ratio of the amount of data that you have to do for teleop training versus human vision?
So during teleop training, the meta training, we take one teleop demonstration and one non-teleop, so one video. But you could probably mix that up. You could probably say, OK, instead of having one video for one teleop, you could probably record 100 videos for one teleop, because you say, well, here's 100 ways of doing that same task. And that might give you more signal, more invariance to learn from. It might be a more efficient data collection scheme. So that, in practice, that's probably pretty clever to do. I don't think we actually did that in this paper. So next idea I want to talk about is actually Josh's PhD thesis work, in some sense, domain randomization. And I think this is, so actually, 2 weeks ago, there was a session in just north of San Francisco, and this was organized by Vinod Khosla from Khosla Ventures, and he brought in Bill Gates and a couple of people, like 6 AI experts, and went around the table, and the question was, what do you think is one of the most surprising results that has happened in the last year or two or something like that? And this is the one that I chose to highlight in that discussion, because I think it's really surprising how well this has worked. So why would you want to work in simulation? Actually, there's so many reasons you'd want to work in simulation. Everybody loves working in simulation. It's less expensive, faster, more scalable, less dangerous, easier to label. But often what you learn in simulation does not work in the real world, and that's kind of the catch. So you get cool demos in simulation, but no real working system. You might say, well, why not just build a realistic simulator? That's actually really hard to do. Of course, in the self-driving space, people are trying. It's a massive market and so forth. But even then, there's still no realistic driving simulator out there, despite people working on it for such a long time. Often also, the more realistic you make your simulator, the more you kind of start paying the same price as you're working in the real world. You might all of a sudden have very expensive compute that you need to pay for, rather than a cheap simulator that is much cheaper than real-world experiments. Another idea that's seen actually a good amount of traction, and is very interesting, is this notion of domain confusion or domain adaptation. And this idea, the idea is that you have your neural network, and you feed in simulated image and real image. You feed it into the same network, and after some processing, at some point in the network, you have a hidden layer, and from that hidden layer, you use a classifier, and the classifier is supposed to say which one of these two is simulated versus real. And if that classifier is not able to succeed, then everything that comes after will generalize between sim and real, because no information has been left in there about sim versus real. It's actually a very interesting approach, and I think we'll see much more of that in the future. But one of the challenges so far has been that that is a training that's very competitive, because that classifier is trying to erase information, whereas the other classifier is trying to extract information. You get this battle of keeping information, erasing it. Here's the domain randomization idea. It's a very simple idea, and you probably would not expect it would work until you actually see that it works. Here are simulated images, and then here's a real-world image. And the task we looked at, and we is really Josh, 99.9% of the work, is can we detect where, let's say, the hexagonal block is in the image? Okay, then maybe a robot can go pick it up. OK, then we'll have simulated images. We'll train on the simulated images, but we'll introduce so much variation so many versions of simulation that the hope is that when it sees then yet another simulator, it also does well because it's seen so many variations already. And then when that yet another simulator happens to be real world, it still works. It's a little crazy because none of these simulators look like the real world, but the hope is that if you randomize enough, lighting, occlusions, viewpoints, textures, color schemes, and so forth, if you randomize that enough, that the only thing left for the network to learn is the thing that you care about, which is finding the hexagonal shape. Because there's no other signal left. You've randomized everything else. Only thing it can learn about is the hexagonal shape. And then when it goes to a real-world image, it'll see that hexagonal shape and find it. Some prior work that happened a little before we worked on this. Sergey Levin and Francesc Sadeghi looked at this for quadcopter flight. So what they did is very interesting. They pre-trained a network on ImageNet. So the network's pre-trained on ImageNet. Then they trained it in these kinds of simulations for a quadcopter to navigate down hallways, the most open space. And it actually then was tested in the real world, and it was able to navigate hallways and buildings in Berkeley. And so we had a generalization there from this kind of simulation, which is more realistic than the ones we'd like to work with, and still pre-trained on ImageNet, so it has some real-world data in it. But it was very surprising. We wanted to see, can you have much less realistic simulation, because you can then simulate much faster, and can you do it without pre-training on ImageNet? We see here is the results. Horizontal axis, number of training examples, logarithmic scale. Vertical axis is average error in the real world. So it's measured in the real world, even though all the training is in simulation. We see that you can localize the block with 1.5 centimeter accuracy. For monocular vision, that is essentially the best you can hope for. If you look at robotics research in the past, when they do really, really good calibration of a single camera view onto a scene, to localize an object, 1.5 centimeters is really, really good. It's able to learn that just in simulation. Then we investigated, okay, what might matter the most? And the thing that mattered the most was the randomization of the textures. So randomizing the textures was really important. This is the number of unique textures used by the renderer. And if you don't use many unique textures, only 10 unique textures, you actually get a pretty high error, like 15 centimeters. Once you have 10,000 different textures used, you get down to about 1.5 centimeter error. Do you need to pre-train on ImageNet? It helps. Blue curves with pre-training on ImageNet. You get there faster, but not that much faster. After about 8,000 examples, you do just as well without the pre-training. And again, this is measured on real world, training only in simulation. Then the next thing, it's kind of funny I'm presenting this because it's all your work, but next thing we did, we meaning again Josh really, is looking at can we make this then grasp objects. So how would we do that? Well, you train in simulation, but how many simulated objects are there? A few thousand in ShapeNet. If you just train on those, it's not going to generalize well to the real world. It's not enough. So the clever idea then was to slice those objects. So any object could become 3 objects, and then recombine these pieces in random ways. That way you generate random objects that look nothing like real-world objects, but locally they are structured like real-world objects. And it turns out if you train on that, you can generalize to real world. I'll skip the table thing here, and I'll show the video. So what we're watching here is a robot that has not seen any real-world data ever and has learned to pick up objects. And so here, seeing new object, screwdriver, never seen that before, picks it up, no problem. Did this approach fully solve picking up objects? No, it did not. I mean, the success rate with this approach is about 80%. Actually, really good success rate compared to other approaches. We never had access to real-world data for this.
So is this RL with?
There's no RL in here. This is essentially grasp point prediction. So in simulation, it learns to predict where it should place the gripper on the object, and then it uses geometric calculations to go there, and then executes it.
What's the, I guess, yeah, how do you know you succeeded?
So in simulation, you know you succeeded because you can simulate whether you pick up successfully or not. And here, we just need to run some tests to validate how well it works in the real world. We're not training anymore. There are things like the Google Arm Farm where you just check after you pick something, is your gripper fully closed or not? Or does it look different from a gripper with nothing in it? And so that's a way to keep training in the real world, but that's not what we did here. Then actually you can take this idea of domain randomization a lot further. You can say I'm going to, instead of what I showed to you so far was about randomizing the simulator such that you learn something that works in every simulator. But it turns out that sometimes the discrepancy between real world and your simulators is too big. And then if you want to build a set of simulators that might be covering enough space so that also work in the real world, they're so different that you can't find anything that works in all those simulators. You can actually change the way you do things. Instead of trying to learn this robust approach that works in all simulators, you can train a recurrent neural network that does few-shot reinforcement learning. So there will be reinforcement learning here. It does few-shot reinforcement learning and adapts to the new simulator on the spot. And so you could train across many, many simulators a neural network that is able to adapt very quickly to the new simulator it's currently in. You do that with many, many simulators, and then you put it in the real world and let it run in the real world. And so this is a robotic hand controlled by a neural network that's been trained only in simulation, but can control the real hand to get the block into the matching configuration shown on the bottom right. And so it's really amazing that, and I think that's really the very surprising aspect here about domain randomization, that it is possible to have relatively simple simulations, either visual or mechanical simulations, but if you randomize enough, and there's some cleverness that has to go into how you randomize, so you randomize enough over things that you should be randomizing over, but retain the essence, they can learn something that can actually work in the real world. Yes? How do you define enough? Yeah, that's a hard question. For some things, I mean, so this project here, in-hand manipulation, we had a project at OpenAI that essentially looked at the same method for pushing objects on a table. And for that project, it took a three-month internship of an exceptionally strong intern to get enough domain randomization in place in the simulator that the real robot could reliably push objects on the table around. But from that, it took another year before, like, I don't know, 10-person OpenAI robotics team did enough to make it work on the hand, which is much, much more complex. And so there's a lot of thought that has to go into how do you randomize, what do you randomize. There's other aspects, of course, in robotics. You need to track the block. And so this is assuming that you have full information of where, you might assume that you have full information where the block is, state information that you need a system to track it. And so there's many aspects in this problem beyond just the manipulation aspect, but it can take a while before you figure out how to do it. One of the things I don't have in here, but that we are doing now and it's starting to work really well, is to also learn that. So we have a new approach to model-based reinforcement learning that effectively learns the domain randomization on the fly. And so the robot just collects data in the real world, learns instead of one simulator, learns a set of simulators, and then meta-learns against that set of simulators to learn something that will work well in the real world. And that can learn to stack Lego blocks now in 10 minutes of interaction with the world, rather than an hour, and probably even more quickly soon. So completely switching gears here, architecture search. I think you've all been training neural nets, so you know that one of the big choices you have to make is to choose the architecture of the neural net, and it has a very big impact on how well it works. Current practice tends to be a machine learning solution consists of data plus compute plus machine learning expertise. Question you can ask, can we turn that into a solution is data plus, let's say, 100 times more compute? And 100 times more compute allows your computer to cycle through ideas, let's say, of architectures, rather than you doing it yourself. It might not be as efficient yet as humans can think through architectures, but that's why maybe 100 times more compute is enough to get there. Google started looking at this. They have pretty much infinite compute. The starting observation was, if you look at the top one accuracy on ImageNet, AlexNet, then GoogleNet, ResNet, VGG, more ResNet, Inception, and so forth, and it became better and better and better. Can we automate this process? If you look at it, what it is networks have, well, they usually have some kind of convolutional layers, but you have to choose how many. You have to choose whether you want skip connections or not. You have to choose the filter sizes, how many filters. Do you batch norm or not batch norm, all those things. And so, but then the question is, maybe you can just have a recurrent neural network which people have used to generate text, generate the textual description of what the architecture is like. So you might say, OK, I'm going to output filter width 5, filter height 3, number of filters 24, and then keep going and build up an entire neural net architecture that way. Your recurrent neural network outputs an architecture. Then you build that architecture. You train your network on, let's say, ImageNet or something. You see how well it does. And now you know how good that architecture is. Then you might say, well, that recurrent neural network that generated the architecture made a bad choice. Let's make a parameter update to it, and hopefully it'll generate a better architecture choice next. That's actually a reinforcement learning problem, because making decisions over time. And so to formulate that as a reinforcement learning problem, to train that recurrent neural network to output strings describing neural net architectures, then here's the controller RNN. So it might choose number of filters, filter height, filter width, stride height, stride width, number of filters for the next layer, and so forth. And at some point it says I've had enough, and this is the full architecture. You can train this with reinforce. I don't want to get into a lot of specifics here, but the bottom line is that you can actually use standard reinforcement learning to train this. This has to be very expensive. Yeah.
Wouldn't this be much more probable to overtrain in some sense?
So that's a good question. I'll answer that in a moment. It's very compute intense, so Google does massive distributed training for this. And after they did it, they found an architecture that they trained on CFAR, which is faster to train on, and then evaluated on ImageNet. So they trained purely on CFAR and found that the architecture they found is reusable on ImageNet in a way that generalizes quite well. And so better than DenseNet, which was the prior best and was a human-designed architecture for ImageNet. So that was a very interesting kind of generalization. They did something similar for LSTMs. Or recurrent neural nets. Can you find a better LSTM cell than the human-designed one? That didn't really work out that well to find something that's better, and people are still using LSTMs. But the image one, people have started to use the kind of essentially the ResNet block that is found by architecture search is often used rather than the original human-designed ResNet block. Here are some numbers on this showing that you can actually also do this if you want to improve the amount of compute, meaning you want to find a neural network architecture that does almost as well as the best one, but uses less compute, so it uses less power than maybe the best one out there. So the key idea here is that architectures are strings. You can have an RNN generate the string and then evaluate, and you can use reinforcement learning to search over. You can also search over activation functions. That original result actually took a really large amount of compute. Then, since then, Google had a new result. What they did there is essentially they said, we're going to have a master architecture that has everything in it. And then the recurrent neural net just selects out things that it doesn't use for the current training run. But it keeps the parameters for everything. And so when it then trains another network, you can have the parameters already, most of them ready to go. It just that a different set of channels is used than in the previous training run, maybe. And that speeds it up drastically. Another thing you could say, well, all this, architecture is one thing. The other tricks you're usually busy with is data augmentation. Whether you're doing domain randomization or any kind of regular training, you want to maybe shift your image or turn it a little bit or make it darker, brighter, squeeze things and so forth, recrop it. And so a lot of machine learning research is on the model, but the data processing really matters too. And so people enlarge their data sets. You have one cat image, you make it into 7 cat images instead of 1. Google, again, because it took massive amount of compute to do this, show that it's possible to learn data augmentation schemes that are more optimal than human-designed ones. And so you would have essentially an image coming in, and then there would be a probability of applying. It would learn that, the probability, optimal probability of applying an equalize, a rotate, a solarize, an equalize, and so forth. And so from that, it would get, as it feeds into the network for training, data augmentation would happen on the fly based on the scheme it learned. It worked quite well compared to human-designed augmentation schemes. And so we have here, for example, wired ResNet on CFAR 100, no data augmentation, 1880, standard data augmentation, 1841, error rate, auto-augment 1709. It's actually better than what humans were doing before. Actually, it's getting very close to human-level error rates on some of these data sets. In this case, ImageNet. Here are some references for that. Now, you might say, I don't have Google Cloud Compute, or maybe you have some compute, but not the same scale that they have. Like, I mean, recently was something like, one machine learning paper can sometimes take more like CO2 emissions than, flying a private jet across the world or something for one of those like massive compute papers. So you might ask yourself some questions about, should we always run these experiments? But for this particular one, we just published a paper that's going to be presented at ICML that does it with 1,000 times less compute and makes it completely practical with any compute that most people have access to. And so the idea here is, so we're comparing here with Google's AutoAugment, and what we did is called population-based augmentation, actually invented by Pieter, who two of you know really well. He came up with this idea. Population-based augmentation does about as well as AutoAugment, and is 1,000x less compute needed. What's different about it? How come we only need 1,000x less compute to do this augmentation? The traditional AutoAugment tries to come up with a fixed policy that you can apply to your data coming through. And so you have a fixed policy, you see how well it works, you update your policy, see how well it works, and keep repeating. So that takes a really long time to find the right policy. In population-based training, what you have is you have multiple policies for augmentation at the same time. You can think of them as hyperparameters, like you have multiple hyperparameter runs happening in parallel. The hyperparameters happen to be augmentation schemes, but you have many runs in parallel. You look at your population after a certain amount of training, and you see which population is doing better on test data. You keep those around, you get rid of the others, you replicate the good ones, and repeat. And so it's like a hyperparameter search, population-based hyperparameter search. What we end up with is not just something at the end. We only do one pass through, actually. We do one run. We end up with is a scheme over time of what is the right data augmentation to use in the first run of training, next run, next run, next run. And so we have a time-varying scheme, which is more powerful than a fixed scheme. And we only need to do one run through everything instead of doing many, many runs. And that's why we get the 1,000x savings in compute. Another direction that I want to quickly highlight here is unsupervised learning. Unsupervised learning, kind of the main idea here is that supervised learning, all this data annotation is expensive. It's, takes a lot of time, a lot of money to get things annotated. Can we use just unlabeled data instead? Because like babies, they just look around in the world, they get no annotation, and then you give one annotation, they know what to do. So, okay, can we learn a network that embeds the data in some way is one of the main ideas. So you take your data, an image gets embedded, and that embedding is somehow better to then train something on than the original pixels. If that's the case, you can learn more quickly thanks to learning and embedding. Or sometimes you train a network, and it's not about the embedding, but it's about the network itself that you use during training, already encoding a lot of features in it, and you'll be able to fine-tune that network to do something with. So the main family of models here are variational autoencoders. They go from image to some code, so it's an embedding model. Generative adversarial networks, they can also go from image to code. Then there are exact likelihood models like autoregressive, pixel CNN, and so forth, and flow models, which are another way to essentially they generate data, and the hope is that the latent vector you start from is like good representation of the data, better than the pixels you end up with. And then there's puzzles, and actually these have worked the best recently. I'll highlight some results in a bit. So generative models think about why, if you want to understand an image, why just take the image and try to process it? Why not just see if we can actually generate images? If we can generate them, that means we have a deeper understanding of them than if all we can do is process them and turn them into something else. So let's say we have a model, a network that we set up to go from a code to an image. Very easy to set up. It's just like a model that becomes bigger, bigger, bigger in terms of what you have in your square that you're generating. This is the images you get. 100 different random codes, grid of 10 by 10, random codes, different random codes use, same network. 100 different images, so that's good. It knows how to generate different images, but none of them are interesting. You start training it. Here's what happens. The codes remain the same. It's one network. Whenever you have a different code, you get a different image. This is when you train on CFAR images. You train on face images. This is what you get. You train on rope. You can get images like this, where you learn how to interpolate between different phases of in a rope manipulation session. You train on faces. You train on faces. This is what you get. So you can learn to generate faces. New random code means new face. And in fact, you can actually play with the variables in the latent code and find variables that correspond to specific things they might care about. Make somebody smile versus not smile, change their age, change their eyes, change their hair, and so forth. Wait, we saw this one. And actually, there's a website that you might have seen, thispersondoesnotexist.com. And that website, whenever you refresh, you get a new person, but a person that doesn't exist. So this person does not exist, but this image was generated by a neural network, and it looks like a real person. Here's another one. If you go refresh again, you'll get yet another one. You don't have to go from a random code to an image. You can go from one image to another one. So this is horse to zebra. And then here's one of my favorite results from the last year is let's say you don't know how to dance, but you want a good dance video of yourself. Well, if a neural network can turn a horse into a zebra, why should it not be able to turn a professional dancer into you dancing? That's exactly what Tingui Zhao and Caroline Chen did at Berkeley. So you use the same idea and turn a video of a professional dancer into themselves. So all they need to do is this simple motion, and that's enough to then turn a professional dance video in you dancing. It's pretty amazing that this is possible. Also has some downsides. Now, you might not trust videos as much anymore as you used to. But it's pretty amazing if you want dance videos of yourself. And it doesn't need to be this kind of dancing. Maybe some of you are more into ballet dancing. If you want that, it's no problem either. Just get a video of a ballet dancer somewhere on YouTube, and you're ready to go. I'm going to skip over to Photoshop 1. You can also do this for text generation. So, once you do text generation, you can also do text reading. So you can give it new text, and you might figure out whether it's positive or negative. So this one here, has been trained on a lot of text, and now reads it character by character and realizes it's quite positive so far. It's apparently a great book, but then the screenplay was not so good. The movie was actually pretty bad, and it turns into red as it reads along in this paragraph. The thing I want to show here is that I think unsupervised learning is actually starting to arrive. And not just with the cool demos I just showed. I feel like the past few years, unsupervised learning has been a lot about cool demos. But the original motivation was to go from needing lots of labeled data to needing a small amount of labeled data, and just a lot of unlabeled data will be enough. Here's a graph. This is a paper that came out, I believe, 5 days ago. Aaron Vandenoord is the main person behind it. This is contrast predictive coding. I'll show you an image of what that actually is in a moment. But let's look at this graph. Number of labeled images per class. This is ImageNet top 5 accuracy. The best supervised ResNet shown in red, and then semi-supervised shown in blue. And what you see here is that by having additional unlabeled data, you can very significantly outperform purely labeled data training. Of course, once you have infinite labeled data, it's not going to be a difference anymore. But especially when you need a low data regime, it's a very big difference. Let me show you a comparison of the different methods that have been most successful at this. They're all little tricks in some sense. The first one, I'll skip the first two. Relative position is one where you train a neural network, you give it 2 patches from an image, and you ask it, where are these 2 patches relative to each other? You might say, oh, this one is maybe 20 pixels north of that one and maybe 40 pixels to the right or something. You train a neural network to do that well, and then after you train the network to do that, all you get to do is to train a linear classifier on the features from that network. And so the hope is that if you define a really good task, that what you learn on that task you don't need to annotate for is a way of turning an image into a set of features where a linear classifier is enough, which means it learned everything there is to learn pretty much about those images. And so a linear classifier gets top 1 accuracy of 36% on ImageNet. Then colorization is where you take an image, you turn RGB into grayscale, and you train a network to turn it back into RGB. You then use that network's final layer and train only a linear classifier on top on labeled data now, and the linear classifier is enough on that kind of features to get 39.6%. Then the original, there's a combo of these four previous ones, which achieved 48.7%. If you train fully supervised, which means you're not restricted to a linear classifier, get a nonlinear classifier, the best performing network out there is 78%. 78%. So people were at 48 2 years ago. Then 1 year ago, CPC came in at 55.4. Oh no, rotational RevNet came in at 55.4. Then the new CPC came out at 61. So it's getting closer very quickly in terms of what you can do with just a linear classifier on top of unsupervised learning, which is really amazing. What does CPC do? The one that works the best, essentially it takes your image and it turns it into a bunch of patches with overlap. And then it'll say, given, let's say, the top row of patches, can you predict a patch at the bottom right? But if you do it naively, you try to predict pixels, it doesn't work. The contrastive part, what it refers to is that instead of trying to predict pixels, what you're given is you're given 1,000 patches, and you're supposed to pick which one of those 1,000 patches is the one that actually sits in that spot. And if you train your network to be really good at correctly picking which one of the 1,000 is the correct one, then it turns out it learns a set of features that is almost as good as features you not there just yet, but getting closer and closer to features that you get from just pure supervised learning on ImageNet. And so that's really, really interesting. Contrastive laws, of course, has many things to choose. The other 999, where do you pick them? Do you pick them from the same image? Do you pick them from a different image? And so forth. There's computational aspects. You feed this as in batch through a GPU. So typically, you pick them from the same mini batch that you feed through. Otherwise, the memory aspects are too complicated. But still, a lot of choices to be made. But the paper from last week shows that it gets extremely close. I mean, again, 61%. Compare that to high 30s it was just 2 years ago to now 61% on top one ImageNet accuracy with a linear classifier on top of these features. So instead of going through lifelong learning, I think we have a couple minutes left, right, Josh? Yeah. Instead of 5 or so. 5 minutes left. Instead of going through lifelong learning, what I'm going to do is skip to, instead of covering another topic, I want to cover a couple of other things here. So let's see. I think if we think about key enablers for AI progress, I think many people would agree. It's data, lots of data, lots of compute to process the data, and you need to think about how to do that. So some human ingenuity is needed. When you think about which problems to work on from a research point of view, you can often think about your problems as falling in one of these two categories. So one category is a category where there's a lot of ingenuity required and maybe a smaller amount of data and compute, or a lot of data and compute and less ingenuity required maybe. And you might say, well, where should I be? If you think about which problem to work on next, and you might say, well, maybe it depends on how smart I am. If I'm very smart, maybe I want to be on the left because then it leverages my smartness more. If I'm less smart, I want to be on the right because it's less needed. But I'm going to argue that actually you always want to be on the right. And the reason you always want to be on the right is that's where the low-hanging fruit is. That's where the new opportunities are. If you're on the left, things that are dominated by just human ingenuity, essentially it's like working in mathematics. And mathematics is a field that progresses, sure, but it requires like extremely rare, exceptional insights to get to the next step. And a lot of low-hanging fruit was actually figured out in the 1500s when people invented calculus and so forth. I mean, deep learning essentially relies on the math of mostly of the 1500s, much less so of the math that happened since. And so if you're over here, that's great, but it's actually really hard. You're competing with everybody from the past, including people from last year, but the year before, but all the way back to Newton and so forth to do something new. Whereas if you're on the right, you might say, well, last year nobody had this data. Last year nobody had the compute to process this data. So actually I could try something nobody could have tried last year. So there might be some low-hanging fruit that I can find relatively quickly, and that will give a cool new result that wasn't possible before. It still requires ingenuity. I'm not saying it requires no ingenuity, but I think it's really good to think about, am I really working on something that people could not have worked on a year or two ago? Because if the answer is yes to that, you have a much higher chance of doing something original than if you work on something where, if you think about it, yeah, 5 years ago people could have worked on it. Then you have a lot of competition already happening in the past that did not succeed. So maybe the problem you're trying to solve is even too hard to solve. So learning to learn is one example where the amount of compute required is pretty high compared to what people had in the past. That might make you ask the question, how much compute do, for example, PhD students at Berkeley use? I would say people often use about 4 to 8 GPUs for local development, and maybe $2,500 to $5,000 a month in cloud compute per person. So it's not zero, but it's also not that crazy. And if you look at the statistics of, OK, who published papers at NeurIPS, ICML, and so forth, if you look at the top publishing places, Google's always first because they have, 10 or 100 times more people doing machine learning research than anybody else. But then second is pretty much always Berkeley, and this is the amount of compute that's needed to get those papers out. I'm hoping to trend towards 10 to 20 GPUs per student and 10 to 20K of cloud compute per month. If anybody wants to donate, please talk to me. I think that's where it will have to be a couple years from now to be competitive. But I think we're good where we are now, but we need to trend towards that. And the last topic I want to cover is how to keep up with all of this. The first thing you might ask is how to read a paper. And I don't want to step through that, but I have some guidelines here that I can share the slides with Josh and Lucas, so you can look at the slides later, on how to read a paper. And it's definitely not reading linearly from start to finish, because usually you waste a lot of time when you do that. It's really important that you quickly go to the back of the paper to see if there's actually any real results in there, and that you have a good understanding of, essentially, you need to have a really good understanding of what's good. I showed you the table for CPC and so forth. You need to understand. Somebody comes up with a paper and says, I did semi-supervised learning, and I got major breakthrough, very cool, and with just linear classifier, I can get top 1% of 25%. It's great. And then you need to know, no, we're already at 61% today. 25% is not great. This paper is probably not that relevant for me. There might be some good ideas, but definitely the results are not that strong. So the ideas did not lead to strong results yet. And so being able to skip forward and understanding whether the results are actually meaningful or not is probably the most important skill to acquire, because then you can filter out many, many papers. But there's a lot more detail that you might want to think about when reading papers, and really quickly rejecting papers that you should not be reading. What papers to read? Just read all the papers is one way. It's really hard. We talked about that at the beginning. It's not really practical. So how do you find which papers to read? Well, here are a few pointers. Import AI is a newsletter by Jack Clark from OpenAI, and it highlights a couple of papers each week. And already summarizes them, and you know that from the summary, this is actually a relevant result. I might want to read the details behind this. Something called Archive Sanity, which is a collaborative filtering system on paper reading. If you're part of that, it can keep track of what papers you like, don't like, what papers people like you, meaning in terms of other papers they've read and that you have also read, what you might want to read based on what they recently liked. And so it's a good way to kind of see suggestions of what you should be reading maybe next. Twitter has a lot of suggestions of people saying, oh, this paper was great, you should check it out. And there are also some groups where there's discussions online on Facebook and on Reddit. The last thing I highly recommend is actually that you form a reading group. If you're going to be reading papers, even if just one other person, you can cut in half the number of papers you need to read. And so if you're going to start reading papers, I would very highly recommend you find at least one other person who wants to read them with you. And you together, you split the work. And you just present it to each other, and you can maybe get presented in 5 minutes what this paper is about. Moreover, they filtered out 100 other papers that they decided were not worth reading, that you didn't have to bother filtering out. And so this is probably one of the most important things if you want to keep up. Thank you.